Okay, so welcome to my talk about auto-differentiation inside ACTS. First, a small overview. I will start with an introduction to autodiff, and then I will show two examples and the implementation of them in ACTS, and in the end, give a small conclusion of this. So, what is autodiff? Autodiff is an algorithmic differentiation technique which allows us to evaluate the exact derivatives of almost any function at a certain point. And almost any function means here you can really use any computer function, like you can use if statements, for loops, recursions, and such stuff. And yeah, it works. A famous application of autodiff is gradient-based optimization in neural networks, also known as backpropagation. But of course, you can use it everywhere where you need derivatives. So how does it work? So if we have a function like the one I show here, either at compile time or runtime, we build up an expression graph of this function, and the derivatives between the nodes, which are some elementary operation where we know the derivatives, are the edges of the graph. And in the end, we apply the chain rule to get our final derivatives, like in this example here. In principle, there are two modes to do this. You can start at the bottom of the graph and go to the top, which is called forward mode, or you can start at the top and go to the bottom, and this is called reverse mode. And while they are mathematically equivalent, there are some algorithmic differences. So there are situations where you should use one or the other one. So I used forward mode in all following examples, and more details on this you'll find in the backup slides, because I don't think we have time for this. So autodiff in C++. So there are many libraries you can use. I chose to use the library autodiff, which is a C++ 17 library. It's header only and has a very nice API and eigensupport. And here you see a small code example. So you define a function f, and then you define an input vector x, which is in this case an eigenvector, and it uses the autodiff type autodiff dual, which enables this auto-differentiation. And then you can use the API function autodiff Jacobian here in this case, and evaluate the Jacobian of f with respect to x at x. So that's a very nice API here. Okay, so now autodiff in ACTS. So ACTS is a modern open source tracking toolkit, and autodiff is there implemented as a plugin for validation of derivatives. And at the moment, there are two applications. So one is the covariance transport in the propagation, and another one is the alignment derivatives. And this one is still in progress, whereas the first one is already merged in. So just a small summary what covariance transport is about. So if we want to propagate a track through a detector, we not only want to propagate the track parameters such as position or momentum, we also want to propagate the covariance matrix, so the errors. And this can be done, like in the green shaded formula, if we know the Jacobian between the two surfaces. And this Jacobian we can build up iteratively through the numerical integration using this D matrix shown in this orange shaded formula. And this is essentially a Jacobian between two stages of the numerical integration. And here we want to use autodiff, and I show you how this is implemented in ACTS. So in ACTS, we have a propagator class, which is a high-level interface for this. And this propagator is equipped with a stepper, which performs an integration step. And this stepper itself is equipped with an extension, which encapsulates the physics and the equation of motion. And if we want to implement this, we need to replace double with autodiff dual in these extensions. So this is in fact done by templating. And then we need to use this autodiff Jacobian function to get our D matrix. And therefore we need this integration step function, which is in principle implemented in the stepper, but we must rewrite it so it can use these autodiff parameters. So how is it done? So here we created a kind of wrapper extension, which takes as a template argument a basic extension and holds internally two instances of this. One instance instantiated with double, and this is responsible for the public interface. So the wrapper externally behaves exactly like the underlying extension. And internally here we instantiate once this extension with auto-diff dual. And we also have this modified integration step function, so we can compute internally the matrix D with auto-diff methods here. And this has a very nice effect that we can use this wrapper extension exactly as we would have the normal extension inside the stepper and the propagator. So the integration is here really easy. So if we look at performance of this, so what we first have to say is that auto-diff is not as efficient as handwritten semi-analytic derivatives, as you see also in the right-hand side plot, which is, I think, quite natural. But it's much faster than this numerical validation, which you see on the right-hand side of this plot using the Ritter's algorithm. So now the test case for this benchmark is the ACTS propagation examples with some reasonable parameters. So this is already merged into ACTS version 1.2.0 as a plugin, and it provides this wrapper extension and a full set of integration tests. So the second example we have is the alignment derivatives. So we have per surface here 6 alignment parameters, which are the center and the orientation of the surface in the detector coordinates. And for the estimation of alpha of these parameters, we need this derivative of the bound parameters with respect to the alignment parameters. And it's, I think that time is not enough to explain why we need this here, but you also find here some more details in the backup slide if you're interested. Yeah, and now how is this done? Here we have the case that one of these derivatives, which is involved in this whole derivative of the bound parameter with respect to the alignment parameters, one of them must be users applied in this case. So we can just pass it to the function as a eigenvector. And this must be users applied because this in principle depends on the equation of motion and the magnetic field. And this is not available in the context here of this function. But the other functions, derivative parts, we can evaluate using auto-diff inside this function. And for this purpose, we define here 2 lambda functions, which represent some transformations from which we can take the Jacobians on the bottom. And then we cast all this to double. And so we get it as eigenmatrices, and then we can combine it like shown in the formula. And in effect, we are done. So as I mentioned, this is in principle just a work in progress. So we have no benchmarks and complete tests of this yet, but we are working on this. And the next steps here are generalizing this, decoupling this from the surface. And also we try to create a similar easy interface as with the convention support with the wrapper extension, so that the user can easily choose which extension, which method you want to use for this derivative evaluation. So now we're already done nearly. Just as a conclusion and outlook, so auto-diff, what it cannot do is it can not outperform analytical calculations. So you'll not get a speed of this, but it is a really easy to use tool if you want to validate derivatives in all kinds of situations. And so also in the future, we want to proceed this and apply this in other fields in ACTS. So for example, we think of the vertex derivatives or something like that. Yeah, and now I'm done, I think.
Perfect. Very nice timing, even a minute ahead. So I hope there are questions. Yeah, already. Josh, go ahead.
Yeah, can you comment on the relationship of this auto-diff library with the auto-diff, which is sort of built into Eigen, which is, I think it's formally marked as unsupported. I don't know if you compared the two at all or considered that one.
Yeah, I'm not really familiar with this Eigen unsupported module. I think it's an RLC-based extension of Eigen, but I must admit I never used it. So because this library I use here is was really easy to use and had all requirements I had. So I cannot specifically comment on that, but yeah, it's based on one of these famous other auto-diff libraries which exist.
Okay, thanks.
Further questions? Maybe I can pose a, well, hopefully straightforward one. So just looking at your performance setup, I mean, is it possible for you to say in like, or rather, are there obvious applications where you would be able to replace current implementations of, say the numerical evaluation that and thereby optimize, not necessarily in ACTS, but elsewhere, improve the code performance quite a lot by using auto-diff?
I'm not sure if I understood the correct question correctly, but it was just that we can replace this numerical validation with the auto-diff validation. Or has I?
No, sorry. I mean, I was wondering if you had in mind other cases where it would make sense to make substitutions like this.
Outside ACTS?
So, inside or outside?
Or inside. So no, I have to admit not really, because yeah, I have to admit not really. It was the project just started with this idea of trying it out if it works here, and then so our approach is then we work through ACTS and look which applications where we can use it. So there's not really a wider scope here, at least from my side. At the moment,
probably in general, like within, this is really tracking code now, and as long as you can write down numerically the integration of the equation of motion for the propagation, you should be able to write down the let's say semi-analytic derivatives. Yeah. They're not trivial, and and it's a great tool to see that the unit tests basically achieve the same results within numerical accuracy. You might get in if we once come to a situation that you could think of an ML module that does for you like a recurrent RNN-based Kalman filter, for instance, where you do where you learn the propagation, yeah, and you predict that. Then you could probably use an auto-diff type style to do the error propagation with it, yeah. But I think this is really super speculative. For the moment, we have put it in as a real great validation tool, which offers a very similar CPU performance already, which I think a great deal on the other side as well.
Okay, thanks. No, that was a useful comment. Okay, I see a hand up from Götz.
Yeah, if it's used for validation, I was wondering, does it also give you some estimate on the precision?
On the floating point precision and numerically? Yeah, I'm exactly not sure. In fact, I don't think so. But I'm really not sure if I can comment on this very educated.
Yeah, I mean, let me also quickly comment here, Götz. The precision here is driven. So in the propagation again, the precision is driven through basically requiring a precision on the stepwise integration. So the adaptive numerical integration, where you already require only to stay within the precision. So then the auto-diff version is exact with respect to the step adaptation you have chosen. To put it that what the module has chosen, because the stepping is still done by a numerical integrator.
Yeah, but I mean, you don't really know what this auto-diff will produce. And I mean, it could produce an incredibly long expression and with a lot of numerical problems, which you just don't know since it's a black box.
Yeah, so generally auto-diff, by the way it's structured in this expression graph, usually produces a pretty efficient numerical code. And so, I mean, I can point you to papers where this has been studied, but this is usually not a concern. So it's more, the expression that you're evaluating, whether or not there are approximations in there. But yeah, for the auto-diff itself, it should be exact to machine precision.
Okay, thanks.
We've probably got time for one more short question, if there is one.